Hello, my name is Pedro Gonzalez, student number 1400654H, and I'm gonna explain how I did this year. First of all, I define some parameters that I'm gonna need to produce the year. After that, I did 4 cycles with the external base, root, and pitch diameter. After that, using the Hayes graphing method, 2 points were obtained to draw the tooth. With these 2 points and the external root and base, I drew the one teeth shape, and using the mirror feature, I get the other face. As we can see, the sketch is fully constrained. Now, extruding the external cycle, I get the base material, and then using the sketch with the tooth, I remove material, and I repeat the operation using the circular pattern. And after that, the axle hole is done. Now I'm going to define different Booleans operation to remove material from the plane face of the gear. Using Booleans operation and different bodies allow us to obtain different gear shapes. By default, I have added the type 4. Now I'm going to change one parameter, that is the number of gear, and Katia is gonna read the spreadsheet and on the shape related to this number. So we can see a new gear. This one is the spreadsheet that I use, but using another bigger, we can get all of these gears with different diameter pitch, different pitch diameters. So I did this using this function catalog. And now I'm gonna show the other elements that I did. The engine block, where angles, align, cylinder diameter, or number of them, among other parameters, can be changed. We can see as well the manifold and the camshafts. We are editable as well.
Hello, my name is Carlos Martinez and I'm going to present my part for the CAD-CAM project. So one of the most interesting features of this piston is the fact that all the dimensions are defined as parameters, and CATIA reads the value of these parameters from an Excel sheet. These values can be changed very easily by the user. So a manufacturing approach has been used to produce this part. So we start from a block of material. In this case it's aluminium, and then the different operations will lead to the final product. In this case, in the first place, what we do is we have to define the basic shape of the piston, and then we want to know the shape of our piston ring, and using the pattern feature of CATIA, we're going to define the number of piston rings on our piston. Then, as we are using a manufacturing approach, we are always removing materials, we never add. So we have to define also how the tools are going to be the ones that we will remove the material from our initial block. So we see the pinhole structure, and then the next 3 operations will remove the interior. So after applying, we see that the interior has been finished. Now we need our pinhole, so that is where the pin that connects our connecting rod to our piston will be located. So we need some lubrication for our pin, so we need additional details like the oil channel groove, and we have to trim the lower part of our piston so it matches exactly with our crankshaft. After applying, this is how it will look like. And then finally, to avoid the knocking of the valves on the piston head, we have to remove some material on the head of the piston. So again, we have to define the position and the geometry of these valves. It will look like this. Now I'm going to show an example of how we can modify all the dimensions. So CATIA will tell us that the design table has changed, so we update our part and we will obtain a new part with the parameters.
Hi, my name is Ignacio Yanconde, my student number is 14075540. I designed the cylinder head using pad, pocket, groove, multi-section solid and remove multi-section solid of CATIA features. The idea of this design was to add and remove material all the time that I needed. This is the main design, the beginning design of the cylinder head. Then I multiply using a mirror extended. I would like to show you now the sketch in the wrist support for the camshaft using the 3D element projections and the different tools for design and drawing in the sketch. I draw the sketch for the rib. It would check is this a constraint. Then for the combustion capacity, I remove the material, and at the same time I decide to create a sketch between the combustion capacity and the piece in order to remove the material for the valve seat. This is the final design of the valve seat. This is the main part of the cylinder head. Using the rectangular pattern and the plane 7, I multiply this part in order to have as many parts as I need for each piston, but at the same time I will use for a parameter for the number of cylinders. Finally, I add and remove material in order to create the walls for the cylinder head using pad and pocket. In order to show you that if we modify the number of cylinders, it is well done parameterized, and we had a different cylinder head for 4 pistons this time.
Hello, my name is Álvaro Fraile, and for this project I developed the crankshaft. One of the best things of this model is the use of several parameters. Each parameter has been linked to an external Excel file. This Excel file also contains several sheets that allows to use the same values to be used in different parts as the crankcase and the crankshaft. In the model, the parameters have been used to define the main features of the part, but also to define the position of the geometrical sets. This allows to create a robust model that can be easily modified from the external Excel file. For the creation of the model has been used the approach of addition and subtraction of material. First of all, I started creating the main journal. From here I developed the whole cramping, which is formed by the first balance and its features, and also the connecting rod shaft. From here I mirror the first balance to create the symmetrical one, and I create the path for the lubrication holes. From here I continue creating the middle journal, and then copying the first whole cramping that is linked, so if one change is made in this cramping will be done in the second one. Then I create the lubrication holes, and from one side I create a station for the connection with the flywheel, with the holes and the pattern of holes. Then for the other side I create the pulley shaft, and then I use a keyway to connect and transmit the torque around the gear transmission. And from here we can see that if we modify some parameters in the Excel file and then we save the Excel file, then CATIA will recognize and then it will show us an advertisement. Then with this, if we update the model, the whole model will be changed as the new values used in the Excel file.
For the development of this project, a V4 internal combustion engine has been chosen. This assembly has been formed with all the parts created by the group members. All the parts have been constrained using the basic restriction as coincidence, contact, offset, parallelism, etc. However, the main trouble was found to create the relation between the cam and the follower. In order to solve this issue, a 2D sketch has been created with the cam profile shape, and a point has been located in the contact area of the valve ending. Then the 2D sketch and the point have been forced to be coincidence, which means that the valve and the cam will be in contact all the time. In order to show that the assembly is properly constrained, some parameters can be changed and the whole system will be updated automatically. However, a constraint analysis can be done to confirm the robustness of the model. In terms of the kinematic assembly, the system presents 0 degrees of freedom, which means that if the crankshaft angle is modified, the rest of the parts will update their position in order to complete the 4-stroke cycle. However, from the dynamic render shown at the beginning of this video can also be verified the correct use of the kinematic joints.